Hey guys, it's John here. In this video, I'm going to explain everything you need to know about sampling for the SAT. This is going to be all the different terms you need to know, all those different minor details, plus how to solve every single sampling problem that you see on the SAT. If you want to know why you should trust me, I've personally scored a 1550 on the SAT. I currently earn the largest SAT community on this platform called Skool.com, and my goal is to make the channel that you're watching right now the best SAT YouTube channel on YouTube. Okay, with that being said, here's what sampling is. Basically, sampling is what happens when you have a lot of people. Like, let's say all these dots represents a different person. You have a lot of people here, and you're trying to find some kind of very specific piece of information about those people. Oftentimes, what they like, what they want, who they are, what kind of things, what kind of categories they fall into, that kind of stuff. But the issue is you have way too many people. Like, let me draw even more than I have here. And so you can't literally get this information from every single one. So instead, you have to get what is called a sample, which is basically just a smaller amount of all these people, and just ask them what they think. And then you can gain information about them that you can hopefully apply to the full thing as a whole. The easiest way you can think about this would definitely be something like an election. If there is a presidential election, let's say in the United States, you might have one candidate, let's say a Republican candidate, and one candidate who's a Democratic candidate. There's obviously like over 300 million people who live in the United States, and many of those people are adults and voters. So it would be very difficult to literally ask all of those hundreds of millions of people who they're going to vote for in this election. But what you could theoretically do is maybe ask a few thousand, or maybe even a couple 100,000 if you have a lot of resources. And then with that information, you can extrapolate information for who is going to probably vote for who when we actually get to election day. It's not as simple as that, but that's the overall basics of what this is. And so let's say, for example, you were trying to find out how many people in the world still know what 6-7 is. This is actually something that really is kind of important for me because I actually own an SAT brain rot YouTube channel. Okay, I mean, maybe it's not really that important, but whatever. So if you were trying to find out how many people in the world know about 6-7 meme, let's say, what you would have to do is you would have to try to find a way that you can basically get some information from a representative group of everyone all in the world. So you can't just get it from people in the United States because that'd be very biased. Not everybody lives in the United States. So you get some from the United States, some from here in South America, some from here in Africa, some from here in Europe, Russia, China, Australia, all these other countries that I'm not remembering to say right now because there's so many other countries in the world. And then if you can get all this data, like maybe a couple thousand from every single place, with that all together, you can maybe say how many people you think still know about the 6-7 kid. And maybe we'll find out information like out of all these people, 30% know what 6-7 is. So what would this actually be saying? Well, if you took all 8.3 billion people in the world and you did 30% of the 8.3 billion, this is the amount of people we expect would know about 6-7. Now, let's be clear about a couple of things here. First of all, this number may not be entirely accurate. Like, there are literally 8.3 billion people in the world. The idea that we can get a perfect representation of all of them is very, very unlikely. What's more going to be the case is that this is going to be a good estimate of how many people know about 6-7, but in reality, it could be a lot bigger or a lot smaller than that. We could even be entirely wrong. It could be a completely different number. Like maybe it's actually like 5, times 10 to the 9th. Maybe that's the actual answer. This is just a rough estimate based off of the data. But of course, it is actually like an educated thing because we actually are using data behind it. It's not just like a pure guess. And another important thing with that you really need to understand is this idea of randomness. For something like this, like I was saying up here, you would need to have a random sample of everybody in the world. And we can kind of see why this would be the case. Because let's say we literally were to just ask 5 and 6-year-olds, or let's say 6 and 7-year-olds, whether they know about 6-7. I'm willing to guess that a lot of these people are much more familiar with 6-7 than if we were to ask a bunch of adults, or if we were to just ask a random selection of people. Many of these people probably have no idea what 6-7 is. Maybe all of these kids know what 6-7 is. So you have to make sure with what you're getting data from is completely random. It's not just a specific subsection of people that is more likely to like the thing. And this also definitely matters if you're doing something like for an election. With my example with Republicans and Democrats with a presidential election in the United States, if you were to go to a state like California, one of the most popular US states, it kind of looks like this if we were to draw it on a map. I guess like kind of like a banana maybe. This is a very Democratic leaning state. So if we just ask people from California, who are you going to vote in the next presidential election, you probably would see a lot more people saying Democrat than Republican. But if you were to go to a very Republican state, like I guess that'd be maybe someplace like Texas, this is, a mock, okay, that's pretty bad, Texas. But yeah, Texas, you'd probably see almost everybody's there is saying Republican. Okay, not really almost everybody, but at least a lot more people would be saying Republican than Democrat. So you got to make sure that you are doing something random. So for that example, I would need to just get people from all over the United States rather than from just any one specific state. So randomness is key. And another thing that you have to really pay attention to here is stuff like bias. There are many different types of bias that can really badly influence the data that you're collecting here. For example, what if we just asked people in the city whether they know about 6-7 and completely skipped everybody in the rural places in the world? We'd probably get a pretty bad estimate here as well, because probably people in the city, they might have more access to internet, they might have more access to just different people, and so they probably are more likely to know about 6-7 than somebody who's like living, in a place maybe without even internet connection. So that could hurt the reliability of our sampling. Also, what if we were to just ask people and say, hey, do you want to be in our survey? And they say yes or no, and then if they say yes, then you ask them, hey, do you know what 6-7 is? That would also have kind of an issue here, because if we just ask people if they want to be in the survey, they could just say no. And maybe there's some kind of situation where people who are more likely to say no are also the people who are more likely to not know about 6-7. So you have all these people, like let's say we ask all these people, and let's say these two people, they'd say no to being in the survey. They don't want to be in it, but everybody else does. Maybe these people who said no, maybe there's something connected with saying no and also not being a big 6-7 fan. Like probably if you don't know what 6-7 is, you're probably someone who's older, you're probably someone who's more mature, let's be real. And so you probably would not really want to be in a survey from some random person you meet off the street as much as maybe someone who's younger, who's less mature, who just is relaxed and who does know about 6-7. So there could be a connection there. So we could also get some bias here if we just ask people whether or not they want to be in the thing. And then another big issue, what if you just called people and asked them if they know what 6-7 is? Well, you can probably see the issue here. Many people who probably know about 6-7, like these kids, do not even own phones. So you'd be completely missing a huge subsection of the population who probably really is the ones who know about it if you just ask on phones. Likewise, if you just ask on iPads, you probably have a very inflated estimate because probably all these kids do use iPads. And so the important thing to know with all this is I explained here a bunch of different things that could happen. But the truth is you probably can't really completely eliminate any of these. Unless you literally live in a perfect society, which nobody does, you can't literally make sure that you only go to, a perfectly representative sampling of the people. You can't make sure that literally everybody you ask actually does participate, because everybody has free will. Everybody can choose not to be in a survey, obviously. And also, you can't ensure that, you ask the people in all the different ways. There are probably a million different ways I could ask somebody to be in a survey, like phones, texting, websites, YouTube advertisements, paid advertisements, a bunch of different things that I could use to ask people. I can't ensure that I literally use every single possible metric because there's probably just way too much. So bias probably always is going to happen. The big thing you just have to understand is whether it's bias that's so severe that it actually impacts the ability to rely on the study. And we'll see some examples of that in a second. Another thing you should know about this is the margin of error. So as always, whenever doing something like this, like I said before, you can't know for sure if it's going to be exactly the amount that you estimate. For example, if I just go back again to my politics example, if we think about many of the recent elections for president in the United States, like let's even say the 2016 election, if anybody who's watching this video was around then, you would know everybody was really predicting, Hillary Clinton to win that election. But in actuality, what happened is Donald Trump was the winner of that election. And so people were completely wrong about this. Many people had estimates that were completely off from what actually happened. And so the reason why that occurs is because we can never be fully certain about whether what we're saying is true. All we can do is give a really, really good guess, and it could be something different than what we expect. And so what the margin of error does is it basically shows what a plausible range for the data to be in. So for this here, maybe we discover that 23% of people know what 6-7 is. But according to our data, according to the statistical techniques we use, it could be 4% less than that or 4% greater than that of the amount of people. So it could be 19 through 27%. The big thing to know with this is that we're still not saying that it literally has to be in this range. That's why statistics is so confusing and difficult, because literally something crazy could happen. There could be a huge thing that we're missing, or a huge thing that we missed, a huge mistake we made. It could actually be 16%. It could actually be 6-7%. Who knows? All we're saying here is that it's very likely to be in this range. It's more likely than not that it is literally in this exact range. And one thing you can do to make the margin of error go down is you increase the sample size. So you can just kind of think why this would have to be the case. Let's think about the example with the 6-7. if we literally ask like 5 people whether they know what 6-7 is, we're probably going to get pretty, biased results, because those 5 people, maybe they're kids, maybe they definitely know what 6-7 is, maybe they're, old people who definitely do not know what 6-7 is. So if we just ask 5 people, that would be really bad. But what if instead we asked like 500 people? Well, now there's probably a much higher chance that we actually know what results we're getting. We probably would see a very clear distinction of who knows about it, who doesn't. And what if we ask like literally like 5,000? What if we ask like 50,000? What if we ask 500,000? As we ask more and more people, the chances that we're right just gets higher and higher, because as you ask more people, it's more likely that you're going to get to the people who actually are representative of the full population. It's also kind of like the thing, like if you flip a coin, a regular coin a million times, it's likely to get about 50% heads, 50% tails. And that's not because the coin has a brain in it that's giving itself that probability. It's just because as you do it more and more times, that is pretty much the only 2 options. So that's what's pretty much going to happen. So sample size is good. Another thing that kind of plays into this is this thing known as the confidence interval. This is not really too important for the SAT in its current form, but it's another way you can kind of qualify this information. So what you could say is like, hey, we have a margin of error of 4% with a 95% confidence interval. So what that would be saying is that we're basically 95% sure that it is in between 4% or, 4% higher, 4% lower than 23. We're 95% sure of that. So there's still a 5% chance we're completely wrong, but 95% of the time we believe it's going to be right. And as you can probably guess, if you have a lower confidence interval, you can have a higher margin of errors. And one more really important thing that I should mention here is this idea of cause and effect. So what we've been saying so far is really just getting some data from a population that already exists to find out whether they know about 6-7 or not. But what if you're trying to find causation? What if you're trying to find, okay, if you do some action, let's say if you do X action, will it lead to Y result? You should hopefully be able to see this is different from what we're doing here. We're not saying that anything is causing people's love for 6-7. We're not saying that anything is causing people to know about it or not know about it. But what this might be useful for is if you're like, for example, doing a scientific study. Like let's say you're trying to test a new medication, like let's say medication X, and you're trying to see does it cure disease Y. What you would have to do for this is you would have to, rather than doing what we do here, get a group of people, split them randomly into 2 separate groups. So we have some people over in this one and then some people over in this one. And then you'd have to have one group use medication X and one person not use medication X. So the big thing here is that they have to be 2 separate groups, or I guess you could have more than 2, but yeah, at least 2. And they have to be randomly assigned to each one. So like if you have 100 people, you have to just randomly say, okay, 50 of you go into this group, 50 of you go into this group. The 2 groups thing is pretty important because you want to make sure that if people don't use the medication, they don't get their disease cured. Okay, I mean, theoretically, hopefully you would not be doing that because that'd be kind of unethical if you actually had a cure and you didn't use it. But let's say disease Y is just a disease where people naturally get better from it anyways. Like, if you just wait 5 days, you just automatically get better from it. Then we can't say that X was the key thing that caused this change. And so we have to have some people who don't have the X at all. We can say these people are no X, and then these people are actually X. So we can see, hey, if they don't use the X, will they improve? Will they change? Will they get better? And if they do use the X, okay, will they improve? Will they change? Will they get better? And plus, they have to be random as well. And you can probably see why this would have to be the case. Because what if you just gave all the people with the X one, what if you just chose people who were already improving from the condition? What if you chose people who are already getting better? That's obviously pretty biased because now you're taking people who already were getting better and just giving them X. So it's not the X that was making them get better. It's just that they already were getting better. So making it random solves that problem because now you have them just completely separated, no big differentiator between the 2, nothing causing them besides just this medication X. And so that's what you need for a real cause and effect thing. So everything up here, we can just say that, people, maybe like about 30% of people know about 6-7. Maybe about 50% of people are going to vote for the Republican this presidential election. We can only say that this thing causes something else if we follow these 2 criteria here. And in actuality, there'd be much more criteria than just these 2, but for the SAT, this is really all you need to know. Hopefully that makes sense. I'm going to go through a couple of quick questions here. Keep in mind, I have 8 questions here. Some of them are pretty easy, but definitely, as we go further through it, they get a bit harder and a bit harder. 7 and 8 are definitely the hardest out of these. So definitely make sure you watch the whole thing so you can see all the different stuff that we have involving these problems. Also keep in mind, there's going to be a lot of text for each one of these problems. If it helps you to write out all the information that's being said, definitely do that. I probably won't too much in this video because a lot of the text for this is also fairly simple and straightforward. But yeah, if you want to write out information like for this one, if you want to say 60 and then like 7th, that's totally fine as well. Okay, let's go ahead and solve this problem. So 67th graders were selected at random from middle school. These 60 students completed a survey about the school lunch menu, and 45 said they would want more vegetarian options, which is the largest population to which the results of the survey can be applied. So for a thing like this, you really just have to think back to our example from before. I know I'm using this a lot, but like it really is important. So this here, if we were to just ask people in like the United States whether they know 6-7, all we could say in the end is, do people in the US know what 6-7 is? We cannot say, do people from all over the world know what 6-7 is? Because there are many countries in the world that are not the United States, obviously. So with this example over here, the way you can think about it is that it would literally just have to be the 7th graders in the school, because all we can extrapolate this to is specifically the 7th graders. That's the only people they ask about it. We could go a little bit further than the 60 who were surveyed, because we at least are from this overall population. They said they were chosen at random, but we can only go to the 7th graders. You can't say all students at school because there are probably many grades besides 7th grade at the school. Go ahead and pause the video and try out this one and let me know what you get for this. Okay, so fruit scientists signed and conducted a study to determine whether a new fertilizer increases the yield of strawberry plants. Okay, so we can probably see here that this is more in line of the cause and effect stuff from here. So it says here, for the study, the scientists chose a random sample of 60 strawberry plants from one of the fields at a large commercial farm. So from one of the fields, 60 strawberry plants. Okay, they found that the plants given the fertilizer produced significantly more fruit. Okay, so they found when they gave them X thing, aka the fertilizer, they had a Y result, they had more fruit. What is the largest group to which the results of the study can be generalized? You can probably see here it would be all strawberry plants in the field, because that's where they say it's coming from. It's saying 60 strawberry plants from one of the fields at a large commercial farm. They didn't choose it from multiple fields, so we can't say all the plants in the farm as a whole, and we definitely can't say all strawberry plants like in the world, because there's way more strawberry plants than what's being shown here. But we can say in that specific field, this is what we would find. Again, pause the video and try this problem. Okay, so to determine the mean number of hours per week that residents of a town spend exercising, Marcus surveyed 25 people at a fitness center. For the 25 people surveyed, the mean number of hours spent exercising per week was 6.8, so between 6 and 7, just to use that again. Which of the following statements must be true? Okay, so you got to think about this, and you got to think about this in terms of the bias that I said above here. So if you read that problem carefully, you would see the big issue here. They're literally asking people at a fitness center whether they exercise. So it's kind of like, the same thing if you were to ask specifically just kids whether they know about 6-7. Obviously, kids are going to know about 6-7, and obviously people at a fitness center are going to be exercising a lot. So I would actually say for this one that the sampling method is flawed and may produce a biased estimate, because we don't know for sure if everybody's going to be a fitness center enjoyer. We definitely can't say that the weekly exercise time is 6.8 hours for all town residents, because, definitely there's a lot of people who don't use the fitness centers, probably really biased. This one says here that it should not be made because the sample size is too small. That's not really the big issue. This could theoretically be enough people if it's a really small town. The issue is that it's just really biased. And then D here, the sampling method is not flawed and is likely to produce an unbiased estimate. Okay, it's not unbiased at all. It's at a fitness center, so therefore it has to be C. So this is one of the cases where the bias really would be too much. Like, this is way too much bias to really make it a feasible study. Okay, again, go ahead and pause the video and try this one. To estimate the mean number of hours per week that adults in a city spend volunteering, a research group used a computer to randomly select addresses from a list of registered homeowners. The group successfully surveyed 500 households. For the adult survey, the mean reported volunteering time was 3.4 hours per week, which is most appropriate based on this information. Okay, so it says the mean time is 3.4 because it's too large, the sampling method is biased or is unbiased. I would actually say here again that it would be biased. And you see, this may seem a little bit less obvious than the last one, but if you think about it here, if you have 500 households, that would be completely excluding all the people who do not own a house, obviously. All the people who live in apartments, all the people who, I guess, live with other people, like parents or friends. So all the other people would not be included in this. It's specifically homeowners. Like, very few people in, like, for example, Gen Z own a house these days. So, like, you'd be really excluding a lot of people. So it would be really biased because we do not know people whose homes are excluded. It's not random for the entire population. And there probably is a connection between these two. Like, if you are a homeowner, you're probably more likely to volunteer, maybe because you care more about the community. You actually are, planted within the community, so you must kind of care about it. Maybe there's some kind of connection between just your values. Maybe it's a connection between your wealth. Like, you have more money to buy a home, so you probably can spend more time volunteering than somebody who has to just work 24/7. So all these different things would make me say that it probably is biased, especially out of the choices that we have here. 5. Try this out again and see what you get. So they surveyed a random sample of employees at a large corporation about remote work. Using the data, the researcher estimated that 31% of the employees work remotely at least once per week. The margin of error is 5%, which is the most appropriate conclusion about them at the corporation. Okay, let's look at this first one. It is unlikely that less than 31% of the employees work remotely weekly. So that completely ignores this whole idea of the margin of error. We're saying here that we're not sure if it's exactly at this one mark. It could be below or higher than that thing. So therefore, we should probably just not go for A. B, at least 31%, but no more than 36% of the employees work remotely weekly. That's definitely better, but it has a couple issues. Probably the biggest one is that it's completely ignoring the people below. Margin of error means that it can be either above the number or it could be below the number. So if it's saying there, it's saying that it could be above, but it's completely ignoring that it could be also 5% below, aka 26%. So B also is probably going to be wrong. C, the researcher is between 26 and 36% sure that most employees work remotely weekly. This is so close, but just barely nodded because, again, remember, this is just saying how many people we assume work remotely. That's what the margin of error means. It's the people that we estimate are going to be doing a thing. What they're referring to is the confidence interval. They're saying that the researcher is between this amount sure that they work remotely. That's basically if you were to say that you were 26 to 36% sure that something is going to happen, like a confidence interval, like I said up there. That's not what they're saying here again, so it would also be wrong. And then finally, we have D here. It is plausible that the percentage of employees is between 26% and 36%. This word plausible is a really good word for these questions. That's typically the word that is going to be in the right answer, just, not all the time, but most of the time. So for that reason, that's what we're looking for. It's plausible that can be between this amount, but not 100% sure. Okay, we're almost done. We have question 6 here. Go ahead and pause the video again and try it out. Okay, so a sample of households was selected at random from all the households in a county. Okay, so again, the households, maybe not the best start, but let's see here. Based on this sample, it's estimated that the proportion of households that own a pet is 62% with a margin of error of 4%, which is appropriate. Notice what they're doing here to make it a better question than this one over here. They're saying here specifically the amount of households that own a pet is 62%. They're not trying to pretend like this is representative of every single person in the entire world. They're just saying that the people in this specific country in households own a pet. Okay, with that being said here, it says that we're trying to see which conclusion is appropriate. One, it is plausible, okay, so that's a good word again, that the proportion of all households in the county that own a pet is between 58% and 66%. Okay, that seems very good. So yeah, that definitely would be in the margin of error, so that's probably going to be one of the ones. 2, it is not possible that the proportion of all households in the county that has a pet is 68%. Remember, possible does not mean plausible. If they say it's not possible, that means there's literally no situation in which this could be true. But it could be. We could have a situation like the 2016 election where everybody was just completely wrong about their estimates. So therefore, we cannot say it's completely impossible for this to be the case. We could just be really wrong with our estimates, and it maybe could be the case. 3, if the sample size were increased, the margin of error would be expected to decrease. So this would also be true just according to the graph that I showed you over here. If we make the sample size higher, margin of error goes down. Therefore, it must be 1 and 3 or C. Okay, last 2 here. So we have a researcher who interviewed 375 randomly selected adults in a country and asked about their views on a national holiday. Then they showed the results here. It says the population of the country is 250 million. Based on the sample, what is the best estimate of the difference between the number of adults who somewhat support or strongly oppose the proposed holiday and the number who somewhat oppose or strongly oppose it? We, of course, need to use Desmos for this question. So what I'm going to do, I'm going to find out what the proportion is for each of these two things and then see what that would be out of 250 million. So if we look at the first one, 88 plus 141 for these first two divided by, it would be 375. We get this like 61% number. And then for the other one, we have 96 plus 50 and divide that by 375. And that gives us this other number here. And then it says that it has out of 250 million. So we would take this, so take that and multiply it by, let's say 250. I'll just go ahead and do all of them just to make it simple here. So 250 million. And then I can do the same thing again for the other number. So take this, do that, and then use this one instead and say that times 250 million. So this would be the amount of people who support the thing, and this is the amount who oppose it. And it's saying what is the difference? So I would take this thing, and then I would subtract the second thing here. And we get 55, and all these threes at the end. It's saying here, what is the nearest whole number? And the nearest whole number to that would just be 55. And it also says here to do it in millions. So I just say 55 for my answer. So you can see here, this is the connection between samples and a real population. We're finding this small sample of just 375 people, and then we're using that to find out something about a huge population of people, which again, may not be entirely accurate because, 375 is a really small number compared to 250 million, but maybe it'll at least give us some indication of what people mostly think. Let's try this one now. This is definitely the hardest one of this set. So we're saying here that we have 2 independent random surveys to estimate the percentage of the residents who want a new library. The first survey, they had 184,000 residents, and there was a 44.5% supporting it with a margin of error of 1.8%. Second one, we had 186,000, with the supporting being 49.2% and the margin of error 0.9%. It says, assuming each margin of error is calculated in the same way, what is the minimum possible increase in the number of supporters from the first survey to the second? So just think what's really going on here. So we have this first one with the 184,000 residents, let's say 184 here. We basically want to see what is the maximum amount that could have wanted it in that one, and then what is the minimum amount that could have wanted it in the second one. Hopefully this kind of makes sense, because if we're saying here that there was a lot of people in the first one, then if there's less people in the second one, that would be a smaller number than if we were to say that there's a super low amount in the first one, and then a ton of people started in the second one. Hopefully this makes sense. You'll see why I say that in a second. So we have 184,000 and 44.5. What I'm just going to do is I'm going to say 44.5 plus 1.8 would be 46.3. And so then I would just go ahead and say 46.3% of 184,000, because we were trying to just take the largest possible one for this one. Then I would do the same thing for the other one, except I would subtract it this time. So 49.2 minus 0.9, that gives us 48.3. So we do 48.3% of 186,000. So then all we have to do is we have to just take this number and then subtract the other number here, and we get 4646, which would be P for the answer. Hopefully this one made sense. You're just seeing here trying to make it the biggest possible one that could theoretically be, and the smallest possible one that could theoretically be. As always, if your SAT score is currently below a 1401 to get it above a 1400 before your next test, consider checking the link in the description below to join Mission 1400 Plus. We have a ton of really good resources in here. Plus you can get one-on-one tutoring from me for every single person who joins in here, because we have a credit system where everybody can unlock one-on-one tutoring by studying more and more days. A bunch of other cool stuff in here too, including the full math course, the full reading and running course, and the SAT execution system, where you can actually learn all the strategies you need for the test. That's all for me today. Hope you enjoyed this video. I'll see you guys in the next one, and make sure to always stay Gucci.